Okay, this is lesson 5.6 on related rates. So what related rates is really asking us to do is to look into this word problem situation and dig from our memory of a lot of formulas that we've known in the past. Take a look at how to set up the problem, and then every variable is now changing with respect to time. So a dependent variable is not depending on another variable. Everybody is dependent on time. So what we're doing here is there's a situation and each variable is changing with respect to time, and we're stopping the timer at a certain point and say, all right, at this instant, in this moment, what is the change in volume versus the change in the radius versus the change in the height? So every single variable now has a derivative with respect to time. So that's why it says dv dt, dr dt, dh dt. So in a way, it's very, very much like implicit differentiation, where the variable y had a derivative of its own y prime, but that's really because y was dependent on x, and the y prime really depicts dy over dx. So in these cases, it's really not a good idea to write v prime or r prime, because those really are for the function using the independent variable within its equation, and then that prime is actually the dependent variable over the independent variable. So don't do that. Try to make sure to write something over dt, because these are all changing with time as time goes on. Okay, so the first problem here says we have a right circular cone, and the volume of it is 1/3 pi r squared h, what that you learned in geometry. We just kind of pull the pi and the 1/3 together because they're both coefficients. They're constants, coefficients, so we put them to the front. Okay, and just keep in mind what's a right circular cone. Well, a right circular cone means that it's standing straight up like so, and there's a height here and there's a radius here, right? There are other slanted ones. These are oblique cones, so they're slanted like so. All right, so it says in the first one, how does the change in volume relate to the change in h, to the change in height, if the radius remains constant? So what does that look like? It looks kind of like an hourglass, where the base, the radius is fixed, and then you're piling sand on top, and the sand pile keeps growing taller and taller and taller. So my height is changing, but my radius is not. So that's how you can make it so it's one is restricted and the other is not. So the way I do this is I use color coding to kind of remind myself of what's being kept constant. So pi over 3 is a constant, and my radius is being kept constant as well. So in this case, you can see pi over 3 and r squared are a different color because those are my constant. So now I take the derivative, dv over dt, right? The volume is going to change with respect to time, and then my constant, my coefficient is going to stay, and then the h is going to change with respect to time as well. So in this case, you have the volume changing, and the coefficients, the things that are remaining constant, that's not changing, and then the change in the height with respect to time. This is a warm-up problem in a way. It's trying to kind of show you how to set up the equations, but typically we actually give you values for the change in volume, or the change in the height, or the radius, so you can solve for the missing component. Okay. All right, part B says, how is the volume change related to the change in the radius if height is kept constant? So in this picture, what is happening is my cone, the height is fixed, right? And then it's going out like this is my radius. And it keeps going out wider and wider, so that your radius keeps growing and growing, but your height is remaining constant. So that's this idea in part B. Okay, so then in this case, what is being kept constant is the height. So that's why pi over 3 and h are in the same color, and the radius is the thing that's changing. So we take the derivative. The left side is dv over dt. Pi over 3h is my coefficient. Don't forget to take r squared like a normal variable, so it's 2r, but then radius is changing with respect to time, so 2r dr dt. In my next line, I did clean up a bit. I really like the dr dt by itself, and all the numbers, the numerical coefficients to be on one side. Okay. Now, realistically, when we're growing a cone, it grows both tall and wide. So that's why in the part C here says, now radius and height are none of them are constant. So they're both changing. So in this case, then you have two variables. You have your pi over 3 as your coefficient, and you have your r squared and your h, both are variables. Hence, you need to use product rule because you're multiplying the two variables together. Okay. And so then I remind you then, when you're taking the derivative, you can leave the pi over 3 out. The coefficient can stay outside, and you deal with the product rule on its own. That's a lot easier to deal with in this situation. So then you have your 2r, right, and then dr dt. That's what's happening here. You have 2r dr dt, and then keep your h here because that's the product rule. Then you kept r squared, and then the derivative of the second term dh dt. That is your derivative. Now it's perfectly fine, leave it like this, or you can clean up just a bit, because again, we like to have our dr dt and dh dt, all these rates to be kind of on its own, because then it's a lot easier to solve for them if you're given more information. Okay. All right. Next problem says sliding ladder. A 6-meter ladder is leaning against the wall when its base starts to slide away. By the time the base is 2.5 meters from the wall, the base is moving at a rate of 0.5 meters per second. How fast is the ladder top sliding down the wall at the moment? So best thing to do right now is to draw a picture of the situation. So the situation looks like this. There's a wall, there's your ladder, there's your floor. Now remember, this ladder is falling. It's falling down. It's coming down this way. So it's going to slide down. As it slides down, it's going to slide out on the floor, right? So in this case, you set up your variables. For me, typically what I do is I look at this and say, all right, I see a geometry shape. This is a right triangle. I have 3 sides. The horizontal I label as X, the vertical I label as Y, and the diagonal I label as Z. So this is why these are my variables. Next, I remind myself that I have some information for all 3 variables, or 2, depending on the situation. And then with each variable, there is a derivative. So there's a dx dt, dy dt, dz dt. So we have to look at the problem. Okay, it says the ladder is leaning a 6-meter ladder. So the ladder itself is 6 meters. That means then Z is 6 meters, right? By the time the base is 2.5 meters from the wall, so that means my X variable is 2.5. So the only thing missing here is Y. I don't know why. Okay, and that's okay. We'll figure that out in a minute. Now, it also says that the base is moving at a rate of 0.5 meters per second. That's your dx dt. Keep in mind the ladder itself, the 6-meter ladder, it's not shrinking or extending. It's not changing its length. So dz dt will be 0 in this case. And lastly, it is asking you how fast the ladder top sliding down the wall at the moment. So that's what we're solving for. That's why I put a little red dot there. That's what we're solving for. So the reason why this is a right triangle that is super helpful is because we have Pythagorean theorem. So we're going to use that theorem 2 times. We're going to use it in a non-calculus sense. We're going to use that to solve for my y first. So that is what I'm doing here in this case. I solve for the y first. And keep your answer as exact as possible. So don't round it yet. Just keep it in the root. If you can simplify, go for it. If you cannot, just leave it as is. All right. Then, because I recognize that Pythagorean theorem is the theorem to use, I now take the derivative. So when I take the derivative of this, x squared now becomes 2x dx dt plus 2y dy dt plus 2z dz dt. So when I take the derivative, that's what I'm doing here. Now notice I put the 6 in there already. If you know that 6 is your constant, you can either put z in there and make sure that dz dt is 0 because it's a constant, or you can put 6 in there because you know that that ladder will not change in its length. Therefore, you can put the constant there, and when you take derivative, it equals 0. Either way, doesn't matter, as long as you know that that z term becomes 0. Right. Another thing is, if you recognize that as you're taking the derivative, the 2's will reduce out, you can actually eliminate that in the first step. But at this point, you can go ahead and plug in everything you do know and find out the one you don't know. And lastly, put it in the calculator and get a final result of 0.229, round to 3 decimal places, right? So then answering the question, I do answer the question completely. I said the ladder is sliding at the rate of negative 0.229 meters per second down the wall. Watch your units and watch your signs. The negative means it's sliding down, so that makes sense. If it's sliding up, we're moving up, then it's going to be a positive rate. Okay? All right, in problem number 3, we are flying a kite. Mary flies a kite at a height of 20 meters, and the wind carries the kite horizontally away at a rate of 10 meters per second. How fast must she let out the string when the kite is 30 meters away from her? There are a few assumptions in this problem, but first of all, let's give a little picture here, right? First assumption is that Mary is really flying a kite like on the ground. So either she's holding it on the ground or she's pinning that to the ground. So we're ignoring the fact that there is some ground level difference there, right, for this problem. Okay. Another thing that we're ignoring is we know that a true kite flies up and down, left and right in all directions. But to make this problem work for us, we're going to ignore the fact that the height is going to change. The kite, because it says the kite is flying horizontally. So this kite is just going to fly this way or this way, depending on which way you're looking at. But it's just going to slide back and forth. It's not moving up and down. Kind of silly, I know. All right, so now we can see this is definitely another Pythagorean theorem. We have our right triangle again. And the ground is my horizontal, so that's my x, the height is my y, and the z is my string. So those are my variables, right? What information do I have? I know that the height of the kite is 20 meters, right? The string is let out 50 meters. I don't know what the ground distance is. Also, what rates do I know? I know dx dt is 10 meters per second because it's carrying it horizontally at a rate of 10 meters per second. I also know that I'm assuming my height is not changing. That's why a little hint here, I assume the height is not changing. And then dz dt is looking for how fast the string is coming out when the kite is 50 meters away from her. Okay, same as the problem before, we're going to use Pythagorean theorem 2 times. First time is using it to solve for x, solve for the missing variable. Again, you see that I simplify my x here. You don't have to. You can leave it as root 2100. I like this because it does make my answer a lot easier to work with in the next step. Again, I'm using my Pythagorean theorem, so x squared plus y squared equals z squared in that sense. But keeping in mind that because my height is constant, I don't have to put the y in there. So I can go ahead and put 20 in there and make sure that it's constant, it goes away. Excuse me. I take the derivative and notice that I have 2's on both sides, so I reduce that out. And then I can go ahead and plug in what I know and simplify this down to get my dz dt to be 2 root 21, approximately 9.165 meters per second, answering the fact that Mary must let out the string at that rate to make this work. Okay. All right, another situation here. I have an intersection. 2 buses are traveling away from an intersection along paths that make a 90-degree angle. So you have one going up, one going across, or vice versa, any of the corners, right? The first bus is 300 feet from the intersection, traveling at a rate of 50 feet per second. Second bus is 250 feet from the intersection, traveling at a rate of 65 feet per second. Find the rate of change of the distance between the buses. So again, a diagram of this may look something like this. It doesn't matter that you are labeling bus 1 or bus 2, one vertical, one horizontal. It doesn't matter which one you're labeling as bus 1, bus 2, as long as the rate of that bus is corresponding to the bus. So as long as you don't mix it up. So for you, if you put bus 1 vertical and bus 2 horizontal, it's okay. All right. So in this case, I have my variables here. So I have my bus 1, bus 2, and the distance between them, right? And then what do I know? I know that the first bus is 300 feet away, second bus is 250 feet away. I don't know how far the distance is between them. I also have the rate of each of the buses, and I'm looking for how fast is the distance changing between them. So I'm looking for dz dt. So same as before, we're going to use Pythagorean theorem to solve for my z first, okay? And then I'm going to use the formula, Pythagorean theorem again, to take the derivative and see where I can go from there. When you take the derivative, you notice that there's a 2 on every single term. You could reduce that out, hence my next line here of a very clean equation. And I plug everything I know in so I can finally solve for the rate at which the distance is changing. And that is approximately 80.023 feet per second. Watch your units, read the problem again, make sure you're answering it. Your homework does get a little tricky. Sometimes they give you the information in meters per second, but wants your answer converted to centimeters per second. So again, read the problem, okay? All right, in this one, in number 5, we're changing dimension of a rectangular box. So I just kind of drew a rectangular box. The key point is that this is a rectangular box, meaning that your length, width, and height are all different values. This is not like a square on the bottom and then it's just a rectangle on the sides, right? So this is definitely all 3 different values. So here in the problem itself, I did list it. I tell you what dx dt, dy dt, and dz dt equals to, and at this moment, what x is equal to, y and z is equal to. So let's tackle this. It says, first thing I'm looking at what the change in the volume is going to be. So first thing, set up the equation. How do I get volume of this box? Volume is length times width times height. So x times y times z. You're now taking a derivative. This is the perfect example of using product rule with 3 variables, right? So you're going to have dv dt equals, all right, now you have 3 variables. You start with the first one, dx dt times y and z, right? And then you have dx dt, multiply the y and z variable. Next one will be the dy dt times the other two variables. And then the next one in line will be dz dt times the other two variables. Okay, now you have the setup. You're solving for dv dt. Plug all the values in of the green highlight I have above. And you can go ahead and solve, and get the fact that the change in the volume is 2 cubic meters per second. Again, watch your units, okay? All right, next is looking at the surface area. The surface area of a box like this is, I usually use a room to kind of help me figure it out. You have two pieces, top and bottom. You have the floor and the ceiling. And then you have the front and the back, right? And the front and back wall, and then you have the left and right wall. So you have a good combination of everything. So you have 2 XY, so you have two pieces, the bottom and the top. You have your 2 XZ. XZ is going to be the front and the back, and 2 YZ, that's going to be your right and your left. Okay, so you have a couple ways to tackle this. In class, what I did was I factored out the 2 and did XY plus XZ plus YZ. Or what you could do, what I did in this problem here, I just factor out the 2 of each of the product rule. So again, I don't like to have my coefficient in my product rule. I like to deal with the product rule on its own as much as possible. So this is how I got my next line of dA dt equals 2 and then multiply by the product rule. Right. Now plug in all the values you see, work it all out, and get a very, very, very unsatisfying answer of 0 meters squared per second. So it doesn't mean that there's 0 there. It doesn't mean that there's no surface area. It just means that, okay, I have this box and things are growing in different directions or increasing or decreasing depending on your dx dt, dy dt, dz dt. And then starting and then pause. At this moment, I have a new rectangular box. But shockingly, the surface area of this new rectangular box and the original is 0. The change in the 2 surface area is 0 because somehow with the increase in one and decrease in the other and increase in one, it kind of balanced out. So even though it's a whole new box, the change is 0 because the original and the new one, they have the same surface area. That's why it's possible to have 0 meters squared per second in your change of the surface area. Okay. All right, last one is looking for a diagonal, and it might be a little bit easier to see in this picture. It's basically taking one corner all the way to the other corner like so. That would be the diagonal we're looking for. Lucky for you, we have the equation given to you. So the equation given to you says right here, S is equal to the root of x squared plus y squared plus z squared. It's just a much bigger Pythagorean theorem, basically. Okay, so the idea is not you setting that up, but the idea is you taking that and know how to take the derivative. So don't forget chain rule, right? So S equals ds dt equals 1/2 parentheses, keep everything the same to the -1/2 power. Then you take the derivative of the inside, the x squared plus y squared plus z squared. So that's 2x dx, 2y dy dt. Sorry. So let me go back. 2x dx dt plus 2y dy dt plus 2z dz dt. Another thing you should recognize is that, hey, they all have a coefficient of 2. If you factor that out, it will reduce out this 1/2 really, really nicely. So cleaning up your equation to be something like so. Okay, plug in all your known values, clean up as much as possible, and once again, get a really unsatisfying answer of 0 meters per second. So again, it's just coincidence because of the values we chose that these two answers are 0. But keep in mind your units, right? So the first one is a change in volume, so it's meters cubed. Second one is change in the area, so it's meters squared. This is a change in the length of the diagonal, so it's just meters per second. Okay. All right, last problem here is inflating a balloon. A spherical balloon is inflated at the rate of 10 centimeters cubed per second. How fast is the balloon's radius changing when the diameter is 2 centimeters? Again, we're making a very kind of stretch here because we know that balloon is not spherical, but it's a lot easier to work with a sphere than the egg shape that the balloon is. So we're going to assume that we have a spherical balloon, right? And a spherical balloon needs one unit of measure, which is the radius. So we're looking at the volume of this. So keep in mind, volume of a sphere is 4/3 pi r cubed. And then now let's take a look at the information given to us. The balloon is inflated at this rate. So this is the rate for volume. And I'm looking for how fast is the balloon's radius changing. So I'm solving for dr dt, and I'm given the diameter is equal to 2 centimeters. Okay, so all that, right? So I know dv dt is 10 cubic centimeters. And then given that the diameter is 2 centimeters right now, we can then solve for the fact that the radius must be 1 centimeter at this moment. Okay, now I can take the derivative of the volume function here that I've set up for my sphere. So if you take the derivative, you get dv dt equals 4 pi r squared dr dt. And now I can plug in everything I know. I know my dv dt, and I know my radius is 1 at this point. So go ahead and plug it all in. Clean that up as much as you can, and calculator should give you 0.796 for your answer. So the rate at which the radius is changing is about 0.796 centimeters per second. Okay, that's it.